Okay, I'm Elizabeth Lawrence, your Summit County Commissioner, and I'm so pleased to welcome you to CMC Breckenridge tonight for this interesting event on climate change. So how this came to be, there's lots of us here. Maybe you can raise your hand if you saw Rob speak. We were at Mountain Town 2030. We've got a few of you. Raise your hand. Karn, you were there. Yes, Rick. So we were at Mountain Town 2030 in Park City, Utah this past October. And what it was, the town of Park City decided maybe about a year or two ago that they wanted to really address climate change, but within mountain towns. And they were really committed, and they wanted to set up this summit. And they invited us, and pretty much all of Summit County was there. We had Pitkin County, Vail, all across the state of Colorado. A few places in other states, Utah was heavily represented. We even had Killington, Vermont, some places from the East Coast that are all mountain towns. And we got together to really learn about climate change and understand that our federal government might not be going down a road to address climate change, but we as ski towns can set our own goals and do that. And so it opened the first day with Dr. Rob Davies. And the other day I got emailed some pictures of when we were listening to Rob. And you can see us literally on the edge of our seats with our mouths hanging open, listening to him. And afterwards we all said, we need a drink. So you might, I'm warning you, there's plenty of bars in Breckenridge right after this, and you might want to go to one. But what Rob is going to tell you is fascinating information. A lot of you might know, a lot of you, this might be new information. I don't consider myself a scientist or a mathematician, but I found Rob's talk to be so engaging and really more than that, so important. And I've thought about it ever since October, and the Summit County contingent and all our towns, when we were in Park City, we immediately looked at each other and said, we have to bring him to Summit County. So it turned out he's done a mini Colorado tour this week. He was at Steamboat there in Routt County at CMC and spoke there. Earlier this week, he was in Avon and spoke to a crowd of over 400 people in Avon and Eagle County. And then now he's here with us in Breckenridge tonight. So we are so happy that we were able to bring him. So your sponsors tonight, a huge thanks to HC3, myself and Jess Hoover, who you'll hear from later. We really had a lot of fun putting this together. And Jess is going to tell you about what High Country Conservation Center is doing here in our community to address climate change and how you can get involved. So she has lots of info on that later. So many thanks Summit County government, Town of Frisco, Town of Breckenridge, Town of Silverthorne, Town of Dillon, and Town of Blue River. Please make sure to thank Blue River for their commitment to making sure that you guys could hear about climate change tonight. And really, we're so grateful for CMC, Dave and Heidi, for stepping in to host this and providing this great venue for us to be at. We thought it would be a wonderful place, especially since Rob is a professor himself and he can talk to you at another college. So I'm going to read a little bit about Rob. Okay, Dr. Robert Davies is a physicist and noted science communicator whose work focuses on complexity, global change, and human vibrancy. Over the past decade, Rob has delivered hundreds of public lectures to policymakers, business leaders, civic organizations, and faith communities. And his performance science, theatrical collaboration, which is called the Crossroads Project, Rising Tide, has been performed across the U.S. and in 3 countries. Dr. Davies has served as a scientific liaison for NASA on the International Space Station project, as a project scientist with USU's Space Dynamics Laboratory, and an officer and a meteorologist in the United States Air Force. Thank you for your service. Originally hailing from the Black Hills of South Dakota, Rob is currently Associate Professor of Professional Practice in Utah State University's Department of Physics in Logan, Utah. So please join me in welcoming Dr. Rob Davies here to Summit County. Thank you.
So they were, just make sure we can hear here. Can you hear me in the back there? Okay. So they needed a drink. I think what she forgot to tell you was I was first up at 9 in the morning. So I'm wondering how that went. So thank you very much for hosting me and for inviting me. As Elizabeth just said, I've been doing a tour of Colorado this week, and it's just a stunning place. And I grew up in a stunning place, as you just heard, in the Black Hills in South Dakota. I live in a stunning place in Logan, Utah, and it never gets old for me. And the drive down from Steamboat to Vail, and then from Vail over to here, it's just, I'm quite certain that growing up in such a place seeded me at a very early age with just wanting to understand the world. And it's certainly a place I go to restore myself, and I do that frequently, even if it's just for an hour or two. So as you heard, I have a fairly broad background, kind of done a lot of things in science, and in fact, a friend of mine once told me, "Rob, you're becoming so well-rounded as to be pointless." But it turns out to have been the perfect preparation for what I do now, which is to try to synthesize a very broad range of science and social, not just the physical sciences, but also what we call them the hard sciences, right? Chemistry and physics and biology, but also what I call the harder sciences, the social sciences. And what I study, as you heard, is global change and complex systems, and in particular, interactions between our complex human systems of food and energy and economy, and the complex Earth system, our life support system. So our soil and our water and our climate and life, the biosphere, all the living bits on the planet, and the implications for these interactions for us in the coming decades, for our well-being, for our sustainability, and for our vibrancy. And what we're finding is, of course, I think many of you know that the human systems are not only impacting the Earth systems, but they are disrupting them. And so there's our first topic. But they are disrupting them to such a degree that I've actually renamed this talk, to such a degree that we actually have to talk about this word radical. And so we're going to get to this a little bit later, this notion of defining what radical means in this age of humans. So ostensibly, we're here to talk about climate change tonight. And we're going to do that, but I'm assuming most of you in the room know the basic story of climate change. Maybe not all the details of the science, but I'm not going to focus too much on the actual scientific story of climate change. I'm going to review it, but then we're going to move forward. And what I want to talk about most is something that many of you may not quite grasp yet, and that is the scale of the risks that we're facing from this particular challenge, and also the scale of the response that is required of us if we're going to mitigate those risks and meet that challenge. After we talk about the scale, I want to put this whole issue, and there's quite a prominent blogger, sorry about that, scholar who studies climate change, who actually says climate change is not an issue, it's an era. And I think that's exactly the right way to talk about it. So I'm going to put this era of climate change into a broader context still of human impact on the planet. Because as we work on a response, and you have many wonderful people, I think some of you are here in the room tonight, who are working on this. And as I give lots of talks, not just here in Colorado, but in many places, what I do see is a sea change in the last several years of dramatic intensity and energy being put into this. And so you can be proud of that. But as you move forward as a community in deciding what your role is going to be in addressing it, and even you personally, it's going to be helpful to have a context to put this in, a much broader context. And so we'll talk about that, into which we fit our response. And then finally, because at the end of this, I'm afraid that Elizabeth probably didn't overstate it, the information you're going to hear is hard. And I apologize for that up front. There's no way around it. And we'll come around to a very large opportunity at the end, but it's going to be some hard information. And this is not more hard information. This is a synthesis of all the hard information we're all getting all the time. So think of it kind of packaged in a little box for the next hour or so. But because of that, the scale is large and the response that's required of us is hard. In order to move forward with that response, we need to talk about a mindset. And I'm going to submit to you a mindset that I think that we need to have if we are to actually carry out the response that's required of us. So that's what we're going to do tonight. So let's start with climate change. This disruption of our climate system. And the basics are these, of course, right? As a society, what we do is we emit. We burn fossil fuels to produce energy, to do all the things that we need to do, and we create emissions. Carbon emissions, and we measure these in gigatons, billions of tons of carbon dioxide. Take a note, you're going to need that later. Of course, these emissions go up into the atmosphere and they accumulate. And not all of them stay there. Actually, only about a third of what we throw into the atmosphere stays there. About a third goes into the oceans and is absorbed there, and about a third go into land systems, the plants, and is absorbed there. But nevertheless, a third stays up there and it accumulates. And the measurement that we use to measure how much carbon dioxide in the atmosphere is parts per million. So how many molecules of carbon dioxide for every million other molecules, okay? So those are the two things you need to know. Gigatons of emissions and parts per millions of concentrations. So here's what those concentrations look like going back about 1,000 years. So 1,000 years over here on the left, and then basically today over here on the right. And here's our parts per million on the scale on the left. And what you can see is for most of the last 1,000 years, indeed for most of the last 12,000 years, we've been here at pre-industrial levels of 280 parts per million. But then in the 19th century, we begin burning fossil fuels in earnest, and it starts to climb. And you can see that in the middle of the 20th century, it really takes off. And of course, this is when we become a truly globalized industrial society, to where we are today at 410 parts per million. And carbon dioxide is important because it is a greenhouse gas. And it's one of a number of very important greenhouse gases. It turns out to be the single most important in our climate system. And greenhouse gases, because of their molecular structure, absorb energy that's leaving the Earth in the form of light, mostly infrared light, and trap that energy and keep it in the Earth system and convert it into thermal energy, which is heat, okay? So this is why they're important. And so as we raise the carbon dioxide levels, we expect the temperature to go up, and in fact it has, and here's what it looks like, from the end of the 19th century to the middle of the 20th to today. So this map is a map of temperature change. So as the different places on the map go from the cooler blues to the warmer reds, they're warming up. It's not temperature, it's temperature change. The North Pole didn't suddenly get warmer than the equator, but it is warming up faster. So I'll show it to you one more time. From the end of the 19th century to the middle of the 20th to today. Now, you can see that the entire planet is warming. You can also see that warming is not uniform. But if you average all the places on the planet, what we find is the planet over the last century has warmed a little more than 1 degree Celsius. And most of that has come in the last 40 years. Most of that has come in the last 40 years. And for those of you who are metrically challenged, I understand. You can always convert a temperature change from Celsius to Fahrenheit by roughly doubling it. So that's about a 2 degree Fahrenheit warming over the last century, most of it in the last 40 years. And that may not sound like a lot. We'll put it in context in a minute. But it turns out to be a huge amount, geologically speaking, for the Earth system. Now, this anthropogenic, human-caused global warming then is changing other things, because when you change the temperature in the Earth system, you change everything else. Everything is connected. And I think most of us remember from a basic science class somewhere, or from just gardening, that if you raise the temperature, evaporation intensifies. Roughly speaking, warmer air can hold more water. So as you raise the temperature, evaporation intensifies, but then when you do get a storm, there's more water vapor up there in the atmosphere to come down, and so the precipitation is more intense as well. This is an intensification of the hydrologic cycle, the water cycle. And if this were the only impact of a warming climate, it would be huge, because it has been a very intense impact thus far in our warming. But it's far from the only impact, because as I said, everything's connected. When you change one thing, you change everything else. So you change, for example, the cryosphere, all the frozen bits on the planet. This is continental ice sheets like Antarctica and Greenland, mountain glaciers, frozen sea ice, the polar ice cap, the North Pole, frozen tundra, frozen soil, right? And not surprisingly, it's melting. And we see this on a global scale. You change internal distribution of the Earth's energy, the weather patterns. Here in the Northern Hemisphere, one of the most important bits of circulation is the jet stream. This circumnavigates the Northern Hemisphere in the mid-latitudes, and it is our major storm track. It determines where the storms occur, where it rains and where it doesn't. It's also the boundary between polar air and tropical air. So as the jet stream goes around the Northern Hemisphere, it undulates. And so as it waves, it determines how far north you pull tropical air and how far south polar air sinks. And what we find is as the temperature is warming unequally, as you saw, the jet stream is weakening and getting wavier. So you're pulling warmer air further up in the north. Alaska's been having record warm winters. And you're also pushing colder air much further south than it often does. South Carolina's been having record cold winters. That air isn't any colder than it usually is. It's just in a different place than it usually is because of this. You change storm locations and frequencies, drought intensities and frequencies. Everything about this weather pattern changes. You change internal climate cycles, the best known being the El Nino-La Nina cycle. So this is about energy transfer between the oceans and the atmosphere. We change everything about living systems, where things can live and where they can't, where they can grow and where they can't, when they go dormant, when they bloom, when they migrate. Everything about the living system is changing. The ecosystems are changing. Here in mountain environments, that change is particularly rapid because we have these very rapid climate zone changes as we go up in altitude, and species are now migrating upwards and upwards, trying to maintain their preferred climate. We change fundamentally. Atmospheric chemistry, water chemistry, ocean chemistry, soil chemistry, everything changes. And this then is what we mean by global climate change. Anthropogenic global warming drives climate change. So this is the basic story. That's our review, okay? Tied up into this little package here. Earth is warming due to us, principally from the burning of fossil fuels. It's disrupting the entire planetary climate system. And the last part, which is what we're going to focus on for the rest of the evening here, is that on our current path, this carries with it extreme risks for humans. Human civilization, and for the human ecosystem. Everything that I've put up here is considered in the scientific community as scientific knowledge. We know these things. And in science, what we mean when we say we know something is that it's consistent with many independent lines of evidence, inconsistent with no lines of evidence. That's what we mean. We know this as well as we know anything scientifically. The physics equation that tells me that a molecule of carbon dioxide will absorb a certain wavelength of light and turn it into thermal energy in the atmosphere is the exact same physics equation that allows us to build any piece of solid-state electronics. It's the exact same physics. We understand it extremely well. Okay, so that's the basic story. So now I want to talk about scale. I want to talk about the scale of the risk that we're facing and the scale of the response that's required of us to meet this risk. We can do projections based on physics, not climate physics, just physics. Again, as I said, the same physics that lets us take pictures of our planet from the edge of the solar system. And under different scenarios, the biggest X factor being what we humans choose to do going forward. If we continue on our current high carbon emissions path, we can expect temperature changes across North America by the end of this century, another 80 years or so, of approximately 13 degrees Fahrenheit, average. Those dark reds up by the North Pole are temperature rises of 25 degrees Fahrenheit. This is a completely different planet than we live on today, as far as living systems are concerned. This is no longer the Earth. If we were to get religion, so to speak, right away, and go to a low carbon, very low carbon civilization, we can still expect continued change over here on the left under a low carbon scenario of an additional 4 degrees Fahrenheit or so across most of North America. That is quite substantial. That is not, that's more than we have already warned. still. But as you look at these two, you should look at these as two choices that we are making. These are two possible futures that we are now choosing between. Currently, we're choosing to follow the path on the right. And we are not even close to changing that. Not even remotely close to doing what is required to alter that future and move to the future on the left. Now, this kind of temperature change has all kinds of implications. I'm going to give you just a couple of more projections, certainly of interest here in Colorado and very much in my state now of Utah. Springtime snowpack. This is when the snowpack is at its maximum, ready to start melting, giving us our water. In Utah, and I think the same is in Colorado, most Utahns get most of their water from melting snowpack. So what I'm going to show you, and the darker blues, of course, are the higher elevations, the deeper snow, the lighter whites are the lower elevations, thinner snow. What I want to show you is actual data starting in 1950, and we have it going back actually 100 years further back than that, but I'll just show you the 1950. And then we'll look at projections again under a high carbon scenario. So here's actual data, and as you watch this animation, some years are snowier than others. We know this, right? Certainly. But we always have significant snowpack at the end of the winter that melts and gives us our water. Under a high carbon scenario, by the time we move into the middle of the century, you can see that snowpack is dramatically thinned. And by the time we're in the latter half of the century, it's essentially gone. And this is not hard to understand. As the temperature warms, more of our precipitation comes as rain rather than snow, and so we don't get the snowpack. This in itself is a dramatic impact to those of us who live in the West for the very obvious reasons that we can think of. And for some reasons that are not so obvious, I'll get to in a moment. One more projection on soil moisture. So this takes into account projections of both temperature and precipitation changes. And it turns out you can get yourself into a kind of a perverse situation where you're getting moderately more precipitation and the soil is still drier. And again, that's because when you raise the temperature, evaporation intensifies. And it's a big change. It's a nonlinear change. Raise the temperature a little, evaporation goes up quite a lot. So this first one is a moderate carbon scenario, meaning we're somewhere between getting religion and not, so to speak. As the different places on the map get browner, they're getting drier. As they get bluer, they're getting wetter. So you can see substantial drying through the middle of the mid-century, still more drying in the second half of the century, but it's tapering off, hopefully, as we start to get a handle on the carbon emissions. There's one thing I forgot to mention with that temperature graph, our two choices. It's not just the temperature that's different, but then what happens after 2100. If we're on the low carbon track that I showed you, those temperatures by the end of the century have leveled. And atmospheric CO2 concentrations have leveled as well. If we're on that high track, it's quite probable that temperatures are not leveled at that point. We continue to go up after 2100, actually quite dramatically. That's just where we ended the projections in these studies. Okay, so that's drying under a moderate emissions, again, hopefully leveling by the end of the century. Under a high emissions scenario, also substantial drying by the middle of the century, but then dramatically enhanced by the end of the century as the temperature change really starts to kick in and feedbacks start to elevate that and accelerate it. Now, I haven't given you any numbers here. I'll just tell you that the broad spectrum of people who study these kinds of projections, from physical scientists to agronomists to farmers to social scientists to defense planners and public officials, refer to the situation on the left as dangerous and the situation on the right as catastrophic. And that term is being used fairly precisely, meaning unadaptable. Not unadaptable by humans, but unadaptable by human civilization. Because while we humans are incredibly adaptable and highly resilient on an individual level, our human civilization, in fact, is very finely tuned to the climate that we are in. Where we grow our food, how we get our water, where we locate ourselves. To kind of drive that point home, we're going to connect the dots on this picture. Each dot there represents a city on the planet on a coastline with a population of 1 million people or more. On our current trajectory, we're looking at sea level rises by the end of this century as high as 2 meters, and it doesn't stop there if we're on that trajectory. 2 meters of sea level rise displaces 200 million people. 2 meters of sea level rise annually floods 600 million people through high tides and storm surges. So now we get a sense of the less, maybe not quite so obvious impacts of climate change. It's not just that you can no longer grow your food, which is certainly bad enough, or get the water from where you want to get it. But now imagine tens to hundreds of millions of people on the move, forcibly displaced from where they live. Think about what has happened across the Middle East and North Africa, with between 5 and 7 million people displaced from political disruption, the Syrian civil war, which has been utterly catastrophic, and also major disruptions to previously stable weather patterns across North Africa that have driven people off the land. Several million people, of course, have tried to make their way into Europe, and it has been politically hugely destabilizing. And that's with a few million people displaced. Now imagine hundreds of millions. And we start to understand why the US Defense Department over the last 2 decades has issued more than a dozen reports calling climate change the single largest security threat to the United States, because of the massive political instability that it will be expected to produce. And not just outside the United States. Where I live in northern Utah, we actually have a fair amount of water. And I'm wondering what's going to happen when California continues with a few more years of drought and a few million Californians decide they want to move to a place with more water. And we start to see we can already start to see those conflicts arising within the United States themselves, particularly here in the West. So things like these, the disruption due to displacing many people, affecting food systems, our water systems, certainly just temperatures, moving to an entirely new planet, this is the scale of risks that we're facing. We're facing them in the coming decades, and it leads to scientists like Lonnie Thompson, a distinguished glaciologist at Ohio State University, making statements like this. This is not hyperbole. This is not alarmist. It is alarming, but that's because the information is alarming. The knowledge that we have is alarming. And I can find you dozens and dozens, hundreds of such statements from distinguished scientists who study this. Kevin Anderson is another one, deputy director of the Tyndall Climate Center in the United Kingdom. Kevin is a carbon modeler. He looks at carbon scenarios and what they mean for climate and civilization as we move forward. He says a widespread view that a 4C future is incompatible with an organized global community. What he means by a 4C future is 4 degrees Celsius of global average warming above pre-industrial, of which we've already had 1 degree, a little more than 1 degree. He says that such warming is likely to go beyond adaptation. This is that term catastrophic, meaning catastrophic for humans, human civilization. Devastating to a majority of ecosystems, also catastrophic for human civilization, and has a high probability of not being stable. And it's this last statement I want to spend just a little bit more time on, because if you think the risks are high already, let's just take one more look. So looking at past climate data, we can see that the Earth system has exhibited the Earth's climate system has exhibited what's called highly nonlinear behavior in the past. The glacial interglacial cycles are an example of this. You can nudge the climate a little and it doesn't change much, and you nudge it a little and it doesn't change much, and you nudge it a little more and it dramatically changes. And there are different lines in the paleo past climate data that we know that things were very, very different when those lines were crossed. One of those lines is 350 parts per million of carbon dioxide in the atmosphere. The last time the Earth was above that number for a geologically significant amount of time, say a millennium, sea levels were nearly a couple of 100 feet higher than they are today. This was an ice-free planet. Now, certainly that's not going to happen overnight. It takes a long time to melt all that ice, several centuries, perhaps up to 500 years. But the thing about nonlinear systems is they have these thresholds, and there are quite a number of other thresholds that the science suggests are in the climate system, things having to do with tropical forest coverage and how much tundra we have, because that locks up a lot of carbon in the form of methane. And there are quite a number of others I could go through. But the idea is if you cross those thresholds, those tipping points, things change quite dramatically and it becomes essentially impossible to go back on any kind of a human timescale. Or a better way to say it is the probability of doing so is extremely small. And so the risks you're running are extremely high. We often illustrate this notion of stability with the following little simple diagram, a little marble and a dimple. So I disrupt the marble a little bit, and the conditions around it tend to take it back to where it was, conditionally stable. But if I disrupt it a little bit too much, it passes some kind of a threshold there, a tipping point. And feedbacks in the system kick in that accelerate it away from where it was. And as I said, it becomes very difficult to reverse course. You end up in a very, very different state. And we know the Earth's climate system has behaved like this in the past. So we suspect that it can happen again in the future, of course. Now, the notion here is not that if we cross these thresholds, everything turns to fire immediately and we're all done. These things can take time to play out. It's like the movie The Titanic, right? I think you've all seen it. This thing that happened that is the perfect metaphor for all things catastrophic. So they hit the iceberg, right? But it's a glancing blow. It's not so bad. I mean, a few champagne glasses tip over in first class and a few people fall down, but no big deal. And the crew was wiping their brow. That was close because it was this skidding, glancing blow. But the guy who built the boat is on the bridge. And he's looking at the lights. And he says, we got to get everybody off the boat because, and the crew says, well, what do you mean? That was close. He says, no, we can stay afloat with 4 compartments flooded, not 5. And he's looking at the lights and he can see they're flooding 5 compartments. And from that point on, he knows this ship is going to end up at the bottom of the Atlantic. Now, it may take a few hours to play out, which it did, but that's what's going to happen. This is how nonlinear systems are. You cross those thresholds and it becomes exceedingly difficult to reverse the feedbacks that amplify those changes. So here's kind of a graphic of Earth's glacial interglacial cycles. The blue dimple is the colder glacial cycle. It's actually for the last several million years where Earth mostly likes to be, colder. Glacial cycles are something on the order of 120,000 years long. Interglacials, like we're in now, typically last only 5 or 10 or maybe 15,000 years. We're in a particularly long one right now. So that's where we were back before pre-industrially, up there. In an interglacial, our current one, the Holocene, where we've, since the Industrial Revolution, though, we've wandered off into this sort of no man's land. And again, the physics tells us that there is a substantial likelihood that there are tipping points in the climate system that if we cross, take us to a very, very different state down there in this very hot state, what we'll call a hothouse Earth. Now, I say that the science suggests it because we don't have good data for this part of it. For where you go from you're in an interglacial and you just give this huge spike of carbon dioxide. We can run models, but there's uncertainty. The important point here, though, as a civilization, is that this uncertainty is not our friend. The uncertainty about where those thresholds are is not an excuse to not worry about them. When you don't know where the edge is, you stop well before it, right? More uncertainty means more risk when the risks are extreme, as they are in this case. So hopefully this graphic and the notion of tipping points that could be very, very close, probably are, suggests that when you hear reports and you look at the context of these things that are happening, like the intensified tropical storms, and intensified droughts and fire seasons and all of these other big impacts that are happening, and we hear the media talk about it as the new normal. Hopefully this graphic makes clear that on our current trajectory, we are nowhere close to the new normal. We're here, I'm going to reverse for you. We're here, we're going here, the new normal is up here somewhere, and we are nowhere close to it. This is a temperature graph of paleoclimate data going back almost 800,000 years on the left, illustrating this glacial interglacial cycle. You can see we mostly like to be cold, right? And the short spikes are the interglacials. We're in the most recent interglacial over there on the right. The difference between glacial and interglacial is about 10 or 12 degrees Fahrenheit, global average. It takes, even though it doesn't look like it on this graph, but it takes about 10 or 12,000 years for that to warm up. So that's a warming rate of about 1 degree Fahrenheit per millennium. We're warming at something like 30 times that rate right now. We've warmed at 2 degrees Fahrenheit in a century, most of that less 40 years. We've taken a dial on the universe control panel that the climate is very sensitive to, and we just spun it way up. We dialed it up to 11, and now we're waiting to see what happens. And we know what's happening. We're warming up. Now here's where modern humans come on the scene. The anthropologists tell us a couple of 100,000 years ago. So this is the human climate that you're looking at from that arrow to the right. This is all we've ever known. And here's where human civilization comes on the scene, about 10,000 years ago. And there then, that period of stable climate is the Holocene. Now, it's these notion of tipping points then that take us into a dramatically different state, and after we've crossed, becomes exceedingly difficult to reverse on any kind of a human timescale, that lead to statements like this from scientists like this. And this is an absolutely mainstream opinion, I promise you. So that's the scale of the risk. What's the scale of the response that is required to meet that risk? And the equation here is very simple at its highest level. More carbon is more risk. So that allows us to calculate something we'll call a carbon budget. What that means is if you can identify a danger line of, let's say, warming, how much warming above pre-industrial, you can then calculate how much more carbon do we think we can throw in the atmosphere and stay below that line. So scientists, not surprisingly, have been doing this for a number of decades. There was a very large study that was done back in 2012 that calculated a carbon budget for a 2 degrees Celsius danger line. Remember, we've warmed a little more than 1 so far. That budget in 2012 for 2 degrees was about 1,000 gigatons of carbon dioxide, 1,000 billion tons more that we could put up. And I should say that this is for a 2/3 chance of staying below that line. There's uncertainty here, so you run the model many, many times, actually lots of models, lots of times, and you do statistics. And if you ask me, when the risks are this big, 2/3 isn't a particularly aggressive risk management strategy. That's 2 bullets in a 6-shooter, playing Russian roulette. No one in this room is going to pull that trigger. Nevertheless, that's the conditions of the study, and that's the budget. Now, of course, it's been 8 years since then, so we burned up some of the budget, quite a bit of it. However, we've also discovered in the intervening time that the Earth has been retaining energy faster than we thought. Most of it's been sequestered in the oceans and a little bit deeper than anyone thought that it would be at this point. As a result, it appears that our budget, the amount of carbon we can dump into the atmosphere and stay below this, is less, about 25% less. It also appears, however, that impacts to both natural and human systems are piling up bigger and faster than people thought even a decade ago. And so it appears that the cliff is closer than we thought, and so we need to change our thought of what's the danger line. And that's been calibrated to about 1.5 degrees Celsius. Again, for a 2/3 chance of staying below, that's our budget as of 2 years ago. Here's our budget as of this month. And here's how fast we're going to burn through that budget. Less than a decade. So in the news media, when you hear people saying we've got 8 or 10 or 12 years to fix climate change, this is what they're referring to. They're not pulling these numbers out of the air. This is the hard science that's gone into this. To the best of our ability to discern, this is our budget for this danger line. And it's very straightforward to calculate how fast we burn through it. I think it's a mischaracterization, though, to say that we have 10 years to fix climate change. The characterization is that the next 10 years are the most important that any of us will ever live through. The next 10 years are critical. Because once we cross that line, how close we are to the edge becomes very, very foggy. And again, when the risks are this big, we don't want to get anywhere near that line. Now, here's that budget relative to our known carbon reserves. This is coal and oil and natural gas that we've already found and we're already digging up. It's still underground. So the physics, this is not politics, this is not liberal or conservative, this is none of that. This is just physics. Tells us that we can only burn less than 10% of the coal and oil and natural gas we've already discovered. So this is pretty clarifying, I think, for a society, certainly for a fossil fuel company. No need for more exploration. We can only burn 10% of what we've already found. And certainly for a society that continues to subsidize financially to a very high degree the exploration for new fossil fuels. Now, if we include resources that we extract through non-traditional means, meaning things like fracking and tar sands, which we should because we're exploiting them, then the reserves, of course, are much bigger. We have a lot more of that. The physics really tells us that we can really burn only about 5% of what we're exploiting currently. This is just the physics. From a risk management, from any meaningful risk management standpoint, that's our line. Okay, so what does that look like for a society? If we're going to meet that line, if we are not going to exceed that budget, what do we have to do? I mean, what does it have to look like on a broad scale? So this is our emissions. Remember, emissions are what we throw up in gigatons. Gigatons on the left-hand scale. In 1990, the globe, the whole planet, we humans, emitted about 20 gigatons of carbon dioxide in that year. Last year, it was almost 40 gigatons, and it continues to go up. Globally, it went up about 2% last year. Here in the United States, a little bit more. So what we have to do is to peak now and decline. And we need to be to zero by mid-century. As long as that line is not zero, the carbon dioxide continues to accumulate in the atmosphere. As long as we emit it, it continues to accumulate. Even after we peak and start our way down, it continues to accumulate. We've got to get it to zero as fast as possible. Now, a lot of people will call this a radical decarbonization. And this word radical is very important because precisely it just means extreme or big. And that is true. We need a radical decarbonization. But usually we use this term radical pejoratively, right? Meaning irrationally extreme. They're radicals. I would argue that even though it's big, this is a completely rational decarbonization. We have to utterly decouple our civilization from carbon emissions. That is the rational response to this. Precisely, it's radically rational because it is big, but it is not irrational. Here's the next 10 years in hatch marks. This is where we're headed in the next 10 years. If every country on the planet who has signed on to the Paris Accord climate agreement, which is every country in the world except the United States now, adheres to their pledges, this is where we'll be. And this is what is needed in the next 10 years. So clearly the Paris Accord in itself is nowhere close to what is required, but it was never intended to be. It was always intended to be a step, and as things got rolling, you increase your goals, right? Nevertheless, we are nowhere close to meeting this goal. That's the bad news. The good news is we haven't even tried. I mean, if we were really trying, and this is still our path, but we haven't even tried. Okay, that budget I showed you, for the math nerds in the crowd, if you integrate under that curve, there's the budget, the area that I colored in blue. If we wait another year to peak, you burn more of that budget up front, so you got to make it up on the back end. If we had started this rational decarbonization 30 years ago when we absolutely knew we needed to do this, it would have been almost trivial. We've now waited 30 years I don't want to say wait. We have been pushed into what is called, again by another researcher who studies this, predatory delay. There have been very powerful interests that have worked very hard to keep us from meeting this, but now it becomes very, very difficult. And every single year we wait to peak, it becomes not a little more difficult, but a lot more difficult. It is not at all clear that we can, in fact, stay below this budget. It is also not clear that we can't. But meeting this is extremely difficult. What does it look like? Let's look at that decline part. Here's what's required. We need to cut our emissions in half every decade for the next several decades until we're at zero. This next decade is by far the most critical in that. And that means globally a 7% annual decline in our emissions. Globally, a 7% annual decline in our emissions. That is enormous. But there's a wrinkle. Of course there is. And that's this, that not all of us on this planet are equally responsible for the pickle we're in. About 10% of the world's population consumes 50% of its energy. About 10% has about 50% of the world's material and energy footprint, is the way we say it. And the top consumers, hyper-consumers, the top emitters are extreme. If the top 10% of carbon emitters and consumers, think of it this way, in the world, if those top 10% of the people who have the highest emissions were to cut their emissions to the emissions of the average European, which are about half the emissions of the average American, if they were to do that, we're not talking about living the life of an ascetic, we're talking about just going to an average European footprint, that would cut our emissions in one fell swoop by 30%. This is how unbalanced the problem creation has been and is today. The world's top 20% consumers are responsible for 80% of our material and energy and pollution footprint. If we consider the top 1% of the consumers and emitters in the United States, about 3.5 million people, I want to compare that to the bottom 1% of the world's population. So that would be about 75 million people. The people on the left consume 2,500 times the people on the right. That 3.5 million people consume 2,500 times that 75 million people. In other words, it would take 188 billion of the world's lowest emitters to equal the world's highest. There's no way that we can expect that as we try to meet this challenge, we can say to Bangladesh or Myanmar or Sri Lanka, you should be cutting your emissions 7% annually. They're just trying to turn the lights on. We're the ones who are mostly responsible for this, and we're the ones who have the wealth and the resources to deal with it, to figure it out. So this 7% global annual drop really means about a 15% annual global drop for the developed world. That's us. And every one of us in this room is in that top 20%. Most of us in this room are in the top 10%. So this is extreme. There's no question that this is radical, but it is rationally radical. This is what is required, and this isn't right or left, it's just physics. So we have to bend the emissions curve by 2020, have emissions every decade. That means 15% per year for those of us in this room, for our communities, for our world. And the good news for us, the very salient point is this is applicable at any scale, from the home to the community, to the region, to the state, to the nation. Now, if you're sitting there in your chair wondering, what can I do? Which I really hope you are. It probably comes to your mind that how can I reduce my personal carbon footprint for 15%? That's a good thing to do. Fine, yes, let's do that. And it's not that hard for just about anyone in this room. What are the top personal, where do these emissions come from? They come from how we produce energy. They come from how we move ourselves around. They come from how we heat our buildings. They come from how we feed ourselves. Agriculture is approximately a third of our carbon emissions. Industrial animal agriculture is about 80% of that. Can you eat less meat and dairy? Can you eat 15% less meat and dairy this year? And any one of us in this room can do that almost without thinking. Can you do it again next year? Well, now that gets a little harder, but okay. Can you do it again a year after that? It starts to get a little harder still. Can you drive 15% fewer miles this year? Yes, almost certainly. And then the next year, and then the next year, it starts to get harder. Can you fly 15% fewer miles? Yes, but then it gets harder and harder. Why does it get harder? Because the systems we're embedded in fight us. They push us to consume, to hyperconsume, to climb in cars, to climb on airplanes, to eat very highly processed food, which has a huge energy and emissions footprint. The systems push us. So if you're thinking, what can I do? Here's what you can do. Fine, take ownership of the problem. The psychologists say this is great. We have to do this. But you're very limited in how much you can accomplish that way. What you have to do is plug yourself into the systemic changes. And there are many efforts underway, some of which you'll hear about at the end of the night, to change the systems we're embedded in. In Utah, so if we took that carbon budget I gave you and divided it equally among every person on the planet, that would be 44 tons, not gigatons, 44 tons of carbon emissions per person. That would be our lifetime ration, 44 tons. In Utah, the average Utahn, and this is pretty close to what Colorado is and pretty close to the national average, we're a little higher. The average Utahn has a footprint of about 19 tons per year. Same in Colorado. So that means that you're going to burn through your lifetime ration in about 2.5 years. Now, consider this. If you go home tonight, unhook the electricity, turn off the gas, sit in the dark, never go anywhere, eat kale, and decompose on some garden seeds, your personal carbon footprint embedded in the systems in Colorado would be about 6 tons per year, down from about 19. So in other words, if you live an impossible life of an ascetic, you can change the time that you're going to burn through your lifetime ration from 2.5 years to about 6 years. Maybe 7. So in other words, it doesn't take us where we need to go to do that. Do these things, yes, but as long as the systems fight us, there is no way to get to where we need to go. So if it takes you out of your comfort zone, I'm going to have to ask you to get over yourselves. We've got to plug ourselves into systemic change. This is not about finger pointing, saying you're driving an SUV and you're still eating steak and you're flying 1 million miles a year. That's not helpful. We all have different capacities. We all have different situations in our lives. What we do need to do is what we can, and we really need to focus that on systemic change. So you need to, and I'll come back to that a little bit later. Now, this is the part of the talk where you think, okay, the talk is done. Sorry. So that's the scale of the risk that we're facing. That's the scale of the response that is required of us. What is the context into which we need to organize our activities, this response? This is key. Because we're just ginning up right now, really big response. We want to make sure we get it right. Right? You don't want to get 10 years down a big response that's not helping. Okay, so these are graphs of different metrics in the Earth system that are changing from the middle of the 18th century to today. And I don't want you to read the graphs, I just want you to look at the shapes. Just look at the shapes. They're the same shape of the carbon dioxide graph I showed you. In fact, one of them is the carbon dioxide graph I showed you right there. These are trends in our Earth system. This is how our Earth system is changing. And you see that they really kick into this dramatic growth starting in about the middle of the 20th century, when we become a fully industrialized global civilization. We're fundamentally changing. These are all greenhouse gases, very powerful greenhouse gases, atmospheric chemistry. We're fundamentally changing stratospheric ozone. That's ozone depletion, which thank God we caught in the 1980s. That was a close one. Surface temperatures going up. Fundamental ocean chemistry is changing. This is dramatically changing the marine ecology. Our extraction from the oceans skyrocketing, again beginning in the middle of the 20th century. Nitrogen to coastal zones, that's coming from fertilizer that we dump on our fields, that washes into the rivers, that washes into the coastal regions, which creates enormous dead zones depleted of oxygen, into which marine animals swim and die. Massive impact to land systems, again, really skyrocketing roughly in the middle of the 20th century. The evidence to this is overwhelming. Tens of thousands of scientific studies, synthesized and summarized by all kinds of very competent scientists and groups, the Intergovernmental Panel on Climate Change, the Intergovernmental Panel on Biodiversity and Ecosystem Services, here in the United States, the National Climate Assessment, the WWF Living Planet Report, the Global Footprint Network, collaborations of hundreds and thousands of scientists documenting all of this. Here's what's happening in our biosphere. In the last 4 decades, humanity has wiped out 60% of the living creatures on this planet. The ecologists tell us the extinction rate is now up between a factor of 100 and 1,000. We're losing, at the very least, 20 species a day out of an estimated 10 million species on the planet that aren't bacteria. Seabird populations are down 70% since the middle of the 20th century. Elephants are down 70%. African lions are down 90%. Large fish are down 90%. Sharks are down 95%. And this is not from climate change. The ecologists tell us that this impact is somewhere between 12 and 15% is from climate change. Now that will change as climate change gets more extreme. But this is from mass extraction and mass pollution and mass destruction of habitat. This is not climate change. The same systems that are driving climate change are doing this. Should we exceed the 1.5 degree line and move towards 2 degrees Celsius, the marine biologists tell us that we can expect to lose all of the world's coral. This is the tropical rainforest of the oceans, home to at least 25% of the ocean species. This fundamentally alters the marine ecosystem in a devastating way. In the last 3 decades, across Europe, they've lost 3/4 of their flying insects. In the last 4 decades in Puerto Rico, more than 90% of the insect biomass. Again, this is not climate change primarily. So that's what's happening with the Earth systems, not just the climate system, but a much broader picture of the Earth systems. Now let's look at what's happening with the people systems. And you see the same shapes to the curves, right? And it is, of course, this that is driving that. Population screaming up beginning in the 20th century. Real GDP, think of that as a proxy for material and energy throughput to our system. Foreign direct investment, think of that as a proxy for globalization. Not just regional impacts now, but global. And as we look at more additional parameters, the shapes of the curves are the same. Our impact is dramatically growing, roughly speaking, beginning in the middle of the 20th century. The people who study this refer to this period since the middle of the 20th century as the Great Acceleration. And this is important because what you hear often is environmentalists are always crying doom, chicken little, blah, blah, you know. They're always saying the world's going to end. It never does. So why do we care about this now? Why do we need... Something has fundamentally changed. You just saw it in those graphs. We used to be what is often referred to as a small world on an empty planet, meaning the human metabolism, our extraction and consumption and excretion as a civilization into the biosphere around us was small compared to those processes, tiny even. But what has happened quite recently and very quickly is that we've gone from being a small world on an empty planet to being a big world on a full planet. And that means that our human metabolism is now at a planetary scale, and it's swamping the natural systems. It is fundamentally different now than it has ever been. Prompting statements like this in the most prestigious scientific publications in the world. Climate change is just one piece of what Marnovsky is talking about here. And I just showed you another piece, this massive impact on the biosphere. And it has led the world's geologists to rechristen our current geologic epoch from the Holocene to the Anthropocene, the age of humans, because humans are now the single largest driver of change on the surface of the planet. Measurably, demonstrably, definitively. And it has to do with growth. So look at this black little few pixels that I colored in up there. If I were to grow that arithmetically, which means I'm just going to add that same size square every second, let's say, it would take 10.5 hours to fill up this screen. I've done the math, I promise. On the other hand, if I grow it exponentially, and exponential growth means that you grow it by a certain fraction every time period. And what I'm going to do is double it every second. So when we put it up there in the corner, you see it? We're going to start doubling it every second. 1, 2, 3, 4, 5. Hmm. 15 seconds. Imagine that this is the whole of our resources to use. It took 15 seconds to use up all of them. How many, at what time period in that did we look out over the vast expanse of our resources and say, oh my God, we've still got half left? When did that happen?
Right at the final 1 second before.
At 14 seconds. Now, this is the power of exponential growth. On the very hairy edge of doom, everything looks great. I'm serious. I'm giving you some pretty difficult information, and I'm telling you that we're on the hairy edge. And that is not me telling you. This is science, our collective societal knowledge screaming this at us. But it does not feel like that to you guys. It often doesn't feel like that to me. You're going to walk out of here into your regular lives. You're going to drive nice cars. You're going to go home to nice homes. You're going to eat nice meals. You're going to have nice days on the ski slope and vacations to Italy. And I'm not saying that we don't have problems. And for people in this room who have serious problems, I don't mean to diminish that. But you know what I mean. It doesn't feel like we're on the hairy edge. And this is the insidious nature of our problem. We don't feel it, but we have got to respond to it. We have no more time. Now, by the way, economists, are there any economists in the room? Okay. Economists will tell us that this is not a problem. And they use one word to fix everything. What is it?
Technology.
Technology, yes. Innovation is the one that I always hear. We will innovate. The Stone Age, they tell us, did not end because we ran out of stones, right? We find something else to use. And again, that argument had some merit when we were a small world on an empty planet. But it has no merit whatsoever based in physics when we are a full world on a small planet. The physics of this is very clear. Now, but let's just say for a moment, I'm going to grant a magic moment to the economists, and let's say that tomorrow we discover 3 more planets worth of resources. Tomorrow, we figure it out. There is no physical basis for this whatsoever. So, sorry, I'm going to back up. Now, exponential growth, if you grow something at 3.5% per year, which is what the world's economists in Davos right now tell us that we need to do to be vibrant, right? If you grow anything at 3.5% per year, you'll double it in about 2 decades, a little bit more, 22 years. So if instead of doubling every second, I doubled every 22 years, it would have taken 300 years to fill up that screen, half that screen. And then how much longer to fill up the other half? 20 more years, about 2 more decades. Now, we've magically discovered 3 more planets worth of resources. How long to use up the next one? What's the doubling time? At 3.5%, 20 years. Now we've used up 2. How much more time to chew up the other 2? 20 more years. If we can magically do something that is utterly impossible, it buys us a few more decades, and that's it. This is the nature of exponential growth. And so what this tells us, the clarity here is amazing. We have to transform these systems. This is forget climate change. This has nothing to do with climate. Well, the same systems that are growing like this are driving climate change, but the situation is that we are currently overconsuming our resource base at 160%. We need 1.6 planets worth of resources to sustain our consumption as it is. Now, you can spend more than you make as long as you got something in the bank, but at some point, the bank account goes to 0. That's what we're doing now. We're over-consuming our resource base. We are in overshoot. In fact, it's 1.7 planets. And our plan, on purpose, is to, the economists would say, grow ourselves at 3.5%, which will be vibrant. The physicist would say, our plan on purpose is to be over-consuming our resource base by more than 3 planets in 20 years and 6 planets in 40 years. And the relevant thing about all those numbers is they're greater than 1. So we can pretend I hadn't changed the slide yet. So we can put a cap on how long we have to before the wheels start coming off the cart. It's no more than 4 decades, and it's probably closer to 1. And this has nothing to do with climate change. This is the sheer unsustainability of the systems that we have created. And yes, those systems are driving climate change. That's the bad news. The good news is those systems are definitely going away in the next 1 to 4 decades. So, yes, we need to transform these systems to fix climate change, but we need to transform them anyway. And if we don't, they will transform themselves. And it will not be pleasant. And we will end up in a sustainable state. This notion of sustainability is important. There are many sustainable states for humanity on this planet, and most of them are not pleasant. We need to transform ourselves to a pleasant, vibrant, sustainable state. At the moment, we're just waiting for the whole thing to collapse around our ears, and it's coming. And that just sounds so tinfoil, right? I mean, it's overly dramatic. This is just physics. If everyone on the planet consumed as we Americans consume, we would, right now, today, need between 4 and 5 planets to sustain that. So again, some people need more planets than others. And some people then have more capability and more resources and more responsibility to respond. So I told you all of the climate change thing, and that was bad enough. And you try to introduce a little levity. I truly apologize, because if you're feeling pretty sad and pretty in despair at this point, it's understandable. as I said, we are nowhere close to addressing these issues. And the good news is we haven't even tried. And as we try to address climate change, which is certainly the most acute of our problems, because even if you collapse society, which at the moment is our best chance of avoiding catastrophic climate change, seriously, that's a terrible way to do it. But even if you do that, you can sort of imagine humanity arising again at some point. But if you drive us past climate thresholds, there's no reason to believe there's ever coming back to the climate that human civilization needs. So climate change is by far our most acute. But the reason I showed you all that other stuff is as we embark upon big changes to fix climate change, not incremental. This is not about this is not about replacing components in the same systems. We have got to transform the systems. But we have to do it in the context of all this other stuff. We have to understand that. But if you understand it, it opens up doors that you hadn't thought about before. Eisenhower had this great quote, and what he means by this is if you're not finding a solution to the problem you have, you're probably not including all the pieces. We cannot solve the climate crisis without including the other pieces of the systems that are driving it and the other impacts that we have on the Earth system. But once we consider that, then pathways start to open up. And this is the part where I will conclude now and put forward a mindset that I believe is if we can get to where we want to go. And it's not clear that we can. And I don't mean that technologically. To the extent that there are technological solutions to this, we have the technology we need. To the extent that this is a technological problem, we have what we need. We'll get more, and that'll help, but we don't need any more. This is primarily a cultural problem. This is primarily a cultural problem. It's not clear that we can solve that problem. But if we are to do it, I propose that this is a mindset that we need. We need to be in the mindset of an emergency. And I mean this very precisely. An emergency is a situation that requires immediate response to prevent catastrophic outcomes. That is exactly where we are. The problem is it doesn't feel like it to those of us with the most power to change it. But if we can get ourselves into an emergency mindset, pathways open up. So we're in a planetary emergency. What do I mean by that? Very briefly. Let's go back to this notion of radical versus rational, where we talk about radical pejoratively, negatively, right? And I want to redefine this notion of radical. So first of all, let me say what's not radical. Knowing about a crisis and responding to it is not radical. People and institutions who know and respond are not radical. What is radical, irrationally extreme, is knowing and not responding. And so, and now I'm going to put you guys in a really uncomfortable place. Well, an even more uncomfortable place, I apologize. I will posit that what's holding us back in responding to this crisis is not the people with their heads in the sand who absolutely refuse to listen or to hear. What's preventing us from going where we need to go is the people who understand the problem but are not yet responding to it in a commensurate way. And that now includes all of us in this room. And I think many of you probably understood that to begin with to some degree, that we have these problems and they're probably pretty big. But now I'm spelling it out for you. And sometimes I get accused of preaching to the choir in a room like this. And there's a fabulous phrase, and I've tried. I can't find who originated it. Do you know why you preach to the choir?
Because they listen.
To get them to sing. If you're the choir, you need to start singing. We all need to start singing. This is radical. Knowing what we know. This is radical. The fossil fuels have got to stay in the ground. If they get extracted, they will get burned. This is radical. Massive industrial pollution. This is radical. This is radical. Not radical. I would posit that one thing you may consider as a community is actually acknowledging formally that this is an emergency. Quite a number of communities in the world have done that. How many in the room recognize this young woman? Now, there are many, many pictures of youth that I could put up here. Greta is by no means the only youth activist who is doing amazing things, but she has become the face of this, I think much to her dismay. This is when she was 15 and sat down outside the Swedish parliament with a sign that said, "School strike for the climate," because, in her own words, the adults in her life were not behaving in a manner commensurate with what she was actually learning at school. So what good is school? This is not radical. Less than a year later, she's the face of a global youth movement headlining rallies of 40, 50, 60,000 people across Europe. Last October, she was the face of a 7 million person school walkout and strike globally. This is not radical. Not a single person in this crowd is behaving in a radical fashion. This is completely rational, I would posit. The second thing is this notion of what is viable versus what is necessary. And this is again where the mindset of an emergency strips away the accoutrement and is very clarifying. We need to set new goals. And what you do in an emergency is you identify immediately what is necessary, and that is your North Star. It's not about viable. When the house is on fire, you get out. You do everything necessary to get out. That is your goal. Now, to the extent that we need everything we need to do is technologically viable. Again, this is a cultural problem, and we often talk about, well, yes, we should do that, but it's just not politically viable. It's just not politically viable. So, for example, if I told you that we need to ban, I'm not actually telling you this is true, but suppose I did. Suppose I said we need to ban the production and sale of all new automobiles. Does anybody in this room think that this is politically viable? We did it. In December of 1941, Congress passed a law and the president signed it banning the manufacture and sale of all new automobiles. They said, GM and Ford, you're making tanks, you're making airplanes, you're making shells, you're making artillery, you're making trucks and jeeps, everything we need to meet this emergency of World War II. Everything in the country was rationed. Fuel, flour, rubber, metal, you name it. People bought war bonds. People enlisted in the military by the millions. What was necessary is what defined it, and then that made things politically viable. So we have to identify what's necessary, and making it politically viable is just another step along the way. And that was only possible, by the way, in World War II because FDR and his cabinet and a number of the industrialists in the country knew that that was coming. For several years, they had been laying the groundwork and drawing up roadmaps. When this war finally hits us, we need to be ready. And that is exactly the situation we're in right now. People have been working on this for decades. We know how to do sustainable food. We know how to do sustainable energy and sustainable economics that are not growth-based. We know how to do that. The roadmaps are there. We need a mindset of an emergency to make this dramatic transformation. We need to ground all the flights and tell the people who are on the airplanes to find their own way home, and you can't get on an airplane again. Politically viable? We did it on September 11th, 2001. The emergency defines what is viable, and so the mindset is critical. We've got to leave this room tonight with a mindset of an emergency, and then pathways open up. Now, I'm not saying it's trivial, that everything just falls into place after that, but it is clarifying. So compared to these things, walkable cities, mass transit, I heard at dinner, we had a conversation tonight, there had been a study to do a train from Denver to Glenwood Springs, but it was decided that it was too expensive. In other words, it was decided it was not politically viable. Maybe in the mindset of an emergency, we get a different picture of that. But most of all, right now, the fossil fuels have got to stay in the ground. If it gets extracted, it will get burned, and we're going through our budget like crazy. That's what's necessary. Now, finally, I hope you didn't come here tonight for hope. Because I have no hope to offer you. I'm serious about that. It is not clear that we can do what is necessary. It is also not clear that we can't. And in the absence of irrefutable evidence that the meteor is going to hit and there's nothing we can do about it, the asteroid, then we have to assume that it's doable, and our job is to identify next steps and take them. That's our job. We have to be cathedral builders. You know, these Gothic cathedrals in Europe, the people who started those cathedrals never lived to see them finished. It took hundreds of years to build some of those. And they knew that. But they said, I don't care, I'm going to do my bit. We have to do our bit. And our bit is to find things that we can plug ourselves into to change systems. So I want to further say that this hope-despair framing is completely wrong. It's not that I don't have hope to offer. What I'm saying is we need to get rid of that framing. Again, in an emergency, you don't hope that you get out of the house that's on fire, you just get out. You don't fall into despair that you're not getting out, you just get out or you die trying. But that's the mindset. It's a mindset of resolve. Winston Churchill, I'm sure you all recognize, and very complicated guy on all kinds of things, but in the emergency of World War II, pretty extraordinary, and I think serves a really great example. So in the spring of 1940, he's just become prime minister. The Neville Chamberlain government that preceded him that had appeased the Nazis for 4 years, much to Chamberlain's dismay, who 4 years before that made the speech about how we are now entering a time of consequences. So the Chamberlain government is collapsed. He's resigned. Churchill is now the prime minister. The entire British Army, the British Expeditionary Force of 350,000 roughly soldiers, is trapped at Dunkirk across the Channel, and they're about to be captured and wiped out. The Chamberlain government had been secretly talking to the Nazis through the Italians to surrender. I mean, England is weeks from invasion. It's done. Their army is gone and trapped and about to be wiped out. It is utterly, in our framing here, hopeless. And then Churchill gets on the radio. I mean, the moment is extraordinary. It is just hopeless. It's done. And Churchill gets on the radio and gives this speech. And it's the famous speech, right? It's the, we shall fight them on the beaches, and we shall fight them on the hills, and we shall fight them on the landing fields and in the cities, and we shall never surrender. And we shall never surrender. That's a mindset of resolve. He doesn't know how, but he's going to figure it out. And of course, with Dunkirk, he did. He called for thousands of civilian vessels, small boats, pleasure craft, yachts, fishing boats to go across the channel, pick up the troops. They rescued over 9 days 330,000 soldiers without the British Navy. And then, of course, took the next step, and the next step, and the next step. And ultimately, we know where it went. It wasn't hope or despair, it was just resolve, and that's what we've got to have. And thank God, we're at the end. I'm going to play for you just a short clip that I think is another even more recent. So this is Apollo 13. The spacecraft is on the way to the moon. It's 1970, I think, maybe 1969, 1970. Partway to the moon, there was an explosion. There's two spacecraft linked together. There's the lunar lander, the LEM, Lunar Expedition Module. And there's the command module. The LEM is what lands on the moon and then brings the astronauts back up, and the command module is what they then descend to Earth in. They're on their way to the moon. There's an explosion. They're losing oxygen. They've lost all kinds of systems. It's an emergency. And the engineers in Mission Control in Houston are trying to figure it out. And let's just be clear, in 1970, all the aeronautical engineers were white men. So here we go. Nerds, which you'll see. So here's a little clip from the movie. We're going to have to figure it out. That's the deal. We've been looking at the data, not for the last hour. We've been looking at the data for many decades. That's the deal. He said, we got to turn everything off. Power is everything. This is what we focus on. We got to turn everything off. Everything else is secondary. That's the deal. For us, it's emissions. We got to turn the emissions off. That's the deal. So we have to identify next steps and take them. We don't have to see the path to the top of the mountain. We just have to identify the next steps and take them and do them in the context of the whole system, this holistic approach that we've talked about tonight. I'll apologize one more time for the heaviness of this, but we just don't have time to feel bad anymore. It's not about hope. If you want hope, act. If we want hope, we have to act. And then that generates hope, not the other way around. Thanks everyone for your attention.
For being here. So earlier we talked about when we first heard him was at the Mountain Town 2030 Net Zero Summit in Park City, Utah. So we were so inspired, your elected leaders and staff of local governments here in Summit County, when we heard Rob and others that, have you ever been to something and you realize it's in a little bit of a crisis and you can't help but over-volunteer yourself? That's what we did. We raised our hand and said, we're going to host the next one. So it's going to be right here in Breckenridge, hosted by all of the towns, Blue River, Breckenridge, Dillon, Frisco, Silverthorne, and Summit County. And we're going to host it here September 29th through October 2nd to be bringing mountain towns together and how we can set non-radical goals and really do the work in our own communities. And we'll have more information on how, as a community, you can be involved. We will have a public event, or quite a few, so we'll let you know as those plans are coming forward. We have lots of community members that are serving on our committee for this. So if you're here, would you guys stand up so people can see? Looking at you, Jesse, Kate, Karen, thank you, all of you. So Casey, yes, stand up, show people. I want people to see these are climate leaders in your community. Scott, climate leaders in your community that are here to say, not only do we understand this, but we accept it. So now I'm going to turn it over to Jess.